All right, this video is about the fundamental theorem of calculus. And the fundamental theorem of calculus is a few different proofs. We've looked at the physics proof. We've looked at the trapezoid area proof. This is sort of just the theoretical general proof of the fundamental theorem of calculus. So say you have a function, we'll call it f of x, and you're trying to find a new function, we'll call it a of x, to help us find the area under the function f of x. So that is the area between the function f of x and the x-axis with the bounds. Here the bounds are 0 and x. So that's what we're trying to discover. Now this function a of x, right, it's a function, so it is going to be increasing or decreasing, but it's going to have a rate of change, and its rate of change is going to be represented by one of these little rectangles. So dA, that's the change in the area function. So that's how this area function, as I go from one point to the next, what's happening to the area function, that's the change in A, the change in area, is equal to just the area of this little rectangle. So this little rectangle, of course, if it were to be infinitely small, would have a width of dx and a height of f of x. So that's how you find the area of a rectangle, base times height. The base being, I don't want to just say change in x, right? Change in x would be if it actually had a width, because it's that infinitesimally small width, that width as the number of rectangles goes to infinity and the width goes to 0, we call it dx. And then f of x is the value of the function at that point. So how dx is changing at that point, the value of the function at that point tells us how the area is changing at that point. If I rearrange this expression, I can divide both sides by dx, and I see that dA dx is equal to f of x. So the way the area is changing with respect to x, right? The change in area over change in x equals the function f of x. Well, change in area over change in x is just how the function is changing with respect to x is the derivative of the area function. So the derivative of the area function is equal to the function we're trying to find the area under. So remember, f of x, if you'll recall, is the function that's graphed right here. And a of x is the function that finds us the area. So the derivative of the function that finds us the area is the function itself. Well, that's great, but usually we know the function itself and we don't know the area function. So if I want to do the inverse of both of these, right? I want to say I know the derivative. What's the original function? I'm going backwards. Well, whenever we practice this a lot, when I said I want the derivative, what's the original function? That's the same as finding the antiderivative. So again, the fundamental theorem of calculus says the derivative of the function, of the area function, gives you the function you're trying to find the area under. But a corollary to that, moving forward, the next piece that will help us is saying that then the area function is equal to the area function, and therefore the integral is equal to the antiderivative. So from now on, when we want to find an integral, we can just find the antiderivative.